Good day, everybody. Today I want to look at Jacobi elliptic functions. So next, we're going to look at a way an ellipse can give us all the values of kunyu, sunyu, and dunyu. So we're going to start with the major axis along the y-axis, vertical, and the minor axis, horizontal, along the x-axis. So we'll have x squared over a squared plus y squared over b squared equals 1, with b bigger than a. If b equals a, you get a circle and you get the regular trig functions. A useful special case is if a equals 1, and sometimes I'll use that, but I kind of want things in full generality. So we can have any ellipse, and our k is the eccentricity of the ellipse, which will be the square root of the major axis squared minus the minor axis squared over the major axis, so for us, square root of b squared minus a squared over b. So if we know a and b, we can get k. And conversely, if we have a k, then we can get the ratio of b to a, or a to b. But b to a will be 1 over the square root of 1 minus k squared. So the eccentricity determines k, or conversely, k determines the eccentricity of the ellipse. So here's two ellipses with the same eccentricity, one with minor axis 1, major axis 5/3, the other with minor axis 1.5, major axis 2.5. So same eccentricity. And so they would work the same. The value of k is the same for both of these. And we can see in the picture how we're going to define sunyu and kunyu. We're going to go straight from the point towards the origin, but where we intersect the unit circle, the x and y value will be kunyu and sunyu respectively. Note, I'm using phi here so we can have it similar to the standard definition of the Jacobi elliptic functions, but phi is essentially the same as the usual polar angle theta. And we can go round and round. So if I look at the major 3 Jacobi elliptic functions, there's 9 others, maybe I'll mention at some point, but the major 3 and the other 9 are just ratios of these 3. Our kunyu, which as we saw was just x over r, so if you go straight towards the unit circle, that will be the value. So x is the point on the ellipse, x over r takes me to right here, and y over r. So if you just divide by r, you're now on the unit circle. So that's kunyu, sunyu, and then dunyu is a over r, the minor axis divided by r. And of course, as I mentioned, the convenient special case, just fix the minor axis to be 1. So dunyu would be 1 over r, but regardless, the most dunyu can be is 1, because that's the least r can be is the minor axis. R can be the minor axis or larger. So dunyu is 1 or smaller. We also define du, and I define u more precisely, but for some work, all you kind of need is that the differential du is going to be r over a d theta. And as I wrote here, when you fix a to be 1, it looks like du is r d theta. And that kind of looks like a length. It would be like a length on a circle or something, but it's misleading. You divide it out by the minor axis, so it really should be a dimensionless quantity. And so really what du is it's just a stretching of theta, as we'll see, and it stretches the bigger r is. I guess I'll continue with the property. So we kind of started over. So defining kunyu and sunyu as x over r and y over r, x and y points on the ellipse, r is the distance, the origin is to that point xy, then r squared is x squared plus y squared. So we easily get this identity. And from the equation of the ellipse, we can solve for x in terms of y is the way to go in this case. Maybe I'll show what happens if you solve for y in terms of x. It doesn't work out as well, but I'll only do the correct way right now. So we'll solve for x in terms of y. So just subtract this, multiply by a squared, and really I just need x squared, so I won't take square roots. So x squared is a squared if I distribute a squared over b squared. And if we substitute that into the formula for r squared, x squared plus y squared, then I get this for x squared. And then I could essentially add 1 minus a squared over b squared times y squared. But that was for k squared, the eccentricity up here, right? So k is this. So k squared is 1 minus a squared over b squared. So I have r squared is a squared plus k squared y squared. And now if I just divide through by r squared, then I'll get 1 on the left. I'll get a squared over r squared plus k squared y squared over r squared. But dnu is a over r, and sunu is y over r. As a reminder, there they are. So we get the same two major properties that we had before. And now for derivatives, I can actually do it through the graphing way. Maybe I'll show that, but if we want to do it a different way through the ellipse, then we'll start with the fact that for any point on the ellipse, right, so if I have a point on the ellipse, x will just be r cosine phi. I mean, that's standard polar equation stuff. So x is r cosine phi, takes me to x from the origin. And similarly, y will be r sine of phi, because phi is essentially the polar angle. So if I'm defining kun as x over r, and I want the derivative kun du, then I'll need the derivative of x over r. So I'll take the differential of both sides here. Differential of cosine theta is negative sine theta d theta, and the differential of x over r I'll just leave as is, because that'll end up being kun. Now sine theta is y over r, so I'll sub that in. And I want du, now remember I defined du as r over a d theta. So to get an r over a, well, I just put an r over a there, but I don't want to change the problem, so I also multiplied by the reciprocal, so this is the same as that. And now this quantity is du, and then I have these two. So I've got this quantity times du is this derivative of x over r. So just divide by the du. And since CNU is x over r, dx over r du being negative y over r, a over r, means d du of kun is negative y over r, a over r. But y over r was sunu, a over r was dunu. So we get the derivatives. The others are done the same way. Take the differential here, multiply by a over r and r over a, so that I have r over a d theta, which will be du. And then this, I have differential dy over r. And just quickly, we get dy over r. Once this becomes du, you divide, is these two things. So d du of sunu, x over r times a over r, which is kunu dunu, based on how we defined the Jacobi elliptic functions from the ellipse. And then there isn't a convenient trig function for a over r, so you can go to a boxed property, well, namely this one, dun squared, and take the differential. Well, actually just take the derivative with respect to u of both sides of this identity, that property, and you pretty easily get the derivative of dun is negative k squared sun kun. So once you have the two properties and the derivative of any of the three Jacobi elliptic functions, you get the other two. And so that's where you get the other two from the other property. So that kind of characterizes the Jacobi elliptic functions. The two properties and then these derivatives, the values. Maybe quickly, it's almost a repeat of the above, of the standard definition. But so another way to get the derivatives. So skip all this. This is just defining here, although you do have to be a little more precise for u. So du is r over a d theta. We could kind of get away with to get the derivative properties more precisely. This other way to get the derivatives, I need u more defined like so. And of course, this will result in du d theta is r over a. Again, properties come quickly. We'll do that. But if we wanted to graph kun u or soon u or dun u, just like I did before on the graphing calculator, well, I can graph, well, I want to graph x over r. But x is r cosine phi. It's r cosine theta, but phi and theta are the same here. So r cosine phi divided by r depends on phi, but in the end it'll cancel. So that'll just be cosine phi. And similarly, soon u is y over r, but y is r sine theta. So divided by r will give me sine theta or sine phi. And then if I want to plot, I have to plot x is u and y is cosine phi. So I would get the derivatives the exact same way as before. If you're graphing y equals soon u, graph y equals sine phi, x equals u, and then find dy dx. And you get this, which of course cosine phi is cn u dnu. So again, here we can see as I go around the ellipse, I'm going around at a constant rate. So going around the circle at a constant rate. But theta and phi are always the same value. You can compute r. This is for the major axis 2.5. So that's as big as we can get. Oops. And the minor axis is 1.5. So 1.5 divided by 2.5 is 0.6. Soon u is 1 here. Kun u is 0. Continue on. So we're getting periodic functions, but they're not the same as the periodic functions of sine and cosine. Again, as a special case, if the minor axis is 1, then all you need is the major axis bigger than 1 to get the ellipse with major axis vertical. Here it is 2.5. So before, I drew the ellipse bigger than the unit circle. The ellipse could be inside the unit circle or partially inside, whatever. But it is convenient to have the minor axis 1. Just don't lose information. So here's a look at same idea, but here as I said, the major axis is 2.5. What I'm going to look at now is interpreting u. So again, for any ellipse, we can solve for r in terms of theta. I almost had it before, but if I redo the work, solve for x in terms of y, sub it in, and we got to this equation before. But now I'll sub in what y is. So before I just divided through by r squared to get that dun squared property. But if I replace y with r sine theta, move it to the left-hand side, divide in square root, we get r in terms of theta, also in terms of the minor axis and the eccentricity. So r of theta of the ellipse with eccentricity k and minor axis a. And we want du to be r over a d theta. That's what will work. So I need u to be the integral, and we'll put the lower limit 0 is the way to go. Upper limit theta. So here is r over a. So u of phi is this integrand, which is the same integrand for the standard definition. And anything can be the dummy variable. So it could be t, or it could be theta, which is r of theta. But we don't want to get too mixed up in that. So I do kind of switch back and forth between theta and phi, just because I like theta for the polar angle. So I kind of like that, but I also like phi to be the parameter to match it with the standard definition. But phi and theta are the same thing. So u is this integral, and so people have tried to interpret this integral. When it's r d theta, they're trying to interpret it as a length. But if it's r over a, you see it's not an interpretation of a length. It'll end up being kind of a stretching. I first thought of it as an average value. So for example, if you compute, if you define the average value, it's the integral divided by the length of the interval. So if I want the average value for any value of phi, it would be this. So I'll look at some graphs shortly, but here's one here. So if you've got your integrand, the average value, r over a, and it's measured in units. So it's r measured in units of the minor axis. Then of course, since I've defined, right, so here's r, so r over a is just this. So if that's the average, it's a running average. As theta increases, it kind of levels off somewhat. But r over a, that running average times theta, would just be this times theta. The thetas will cancel, and we get our standard definition of u. So that's the way I like to think of u. That's the best way I could think of it as u. It's the average of r in units of the minor axis times theta, or phi. Maybe I should have used phi here. And then of course if you take du, it's r over a d theta still. Maybe to look at it more clearly here, there's a graph of r over a for when k is 0.8. There's the integrand, r over a. Or in other words, this is kind of r in units of the minor axis a. And then the running average as phi increases is given by this curve right here. I don't know if this is a good analogy, but if you think the distance a particle has moved, if it has velocity v, you can find by doing this integral. But another way to think of it is, well, if you computed the average velocity, then the distance a particle travels is the time it's traveled times its average velocity during that travel. Yeah, what a brilliant analogy. Again, so if u is the this integral, which is the same as the total phi times the average of r divided by a for that phi, then du will be r over a d phi. And so infinitesimally, u is a stretching of phi or theta by an amount r over a. And then for larger intervals, same thing happens. So if you take any two angles, u at phi 2 minus u at phi 1 is just the integral from 0 to phi 2 minus the integral from 0 to phi 1, which gives me this integral from phi 1 to phi 2, which again I'll think of as the change in phi times the average of r over a over that interval, because then these would just cancel again. So essentially, the change in u for any two phis is the average of r over a for those values of phi times the change in phi. And r over a is always going to be bigger than 1. So as I said, any interval length in u is just a multiple of the length of phi. So here's a look at going around the ellipse. Eccentricity 0.8, major axis 5/3, minor axis 1, of course vertical. And we get our kunyu, sunyu, dunyu based on where we are on the ellipse. It's easy to compute. Phi, r, and x, and y. So all these are easy to compute. U, the only way to compute that is to have that more precise definition or version of U. du is r over a d theta isn't quite precise enough, so you need that integral a little more precisely. But the important thing to notice is that for any phi, we have an r. R changes from a low of 1 to a high of 5/3. Again, I want r in units of its minor axis, which in this case is 1. So again, here's a plot of r in its average, its running average. But here I've done it in not r over a, but r in terms of a, its minor axis. So to have a dimensionless quantity, you do r divided by a, and so you're computing r in units of its minor axis. So it's always got a minimum of 1 when your theta's at 0, pi, 2 pi, etc. So as you cross the x-axis, that's when r is 1. But otherwise, r is bigger than 1. And this is the exact same thing, except before I had it as theta, and now I just changed it to phi, because phi and theta are identical. So those were all with k equal to 0.8. If I change k, you don't see too much difference until k gets up there. Then here's a running average graphed along with r. Right, so eccentricity of, say, 0.91, r gets to be like 2.5 times its minor axis. That was like for this picture. So as I said, there's a stretching going on. And I'll first look at a stretching of uniform amount. So right now I haven't stretched it, and I'm going to graph and stretch sine phi. So here's sine phi, not stretched. So there I am at 2 pi, 6.3 almost. Now, if you want to stretch vertically, you multiply the y value by a constant. If you want to stretch horizontally, you divide, right? So if I want to stretch it horizontally by a factor of 2, I would graph y equals sine of phi divided by 2. But I'm not doing that. I'm graphing it parametrically. So parametrically, actually what I do is I still graph y equals sine phi, but x will be phi if I just graph y equals sine phi. But if I want to stretch it, then I can multiply the x component by 2. So this is the x component of my parametric equation. Right now r is 0, so there's no stretch. Or the stretch is, I multiplied by 1, and y is sine phi. But anyway, so as r increases, I stretch. But this is a uniform stretch. So I'm stretching uniformly. So you get that idea. And that's what the Jacobi elliptic functions are. They stretch, but not uniformly. They stretch based on the value of r in that ellipse. So once again, here's the running average. This time I've got it typed for us too. So it's always bigger than 1. It's 1 at the beginning. Say it's undefined there. I put it as 1. But it increases until you reach, well, until it intersects itself, and then it starts decreasing a little more, then increasing again. It somewhat levels off for the most part, but I won't go to large values of theta. So there's the running average of r divided by a. And this is for k equals 0.8. Let's look at for other k's. Here's b over a. I wrote b over a, probably, but a is 1. So I'm going to fix a to be 1. And so right now b is 1 times a. So in other words, I have a circle. So r divided by a is 1 for every value of theta or phi. But as I increase k, you don't see too much difference there, but stretching it. So the unit circle is graphed, but then I'm graphing the ellipse. So the b value is really b over a. Is see if I go to 0.8 here. right there. So now it's 5/3, or about 1.67. So R over A has bigger values right here. And notice those are at pi over 2 and 3 pi over 2, the multiples of odd pi over 2, odd multiples of pi over 2. And there's like there'll be no stretching right here when we're at multiples of pi. So I only went up to k equals 0.96, but so it's a pretty stretched ellipse. So R over A looks like that. So I'm going to go back to k equals 0.8 and look at the R over A. And I'm going to find the running average. There's actually 80 subdivisions I made here, 20 in each quadrant. So 80 subdivisions, 20 in each quadrant. And I'm going to find the average R in each of those 80 regions. And so it looks like that. So obviously you've got a maximum R over A average in that tiny little delta phi or delta theta. It's almost 1.67. It's not centered at pi over 2. That's only an endpoint. But so you can get closer to 1.667, 5/3. But so that would be where it's a maximum. But the minimum is always bigger than 1 for any positive subinterval. It's pretty close to 1, just about 1. So what the graphs of the Jacobi elliptic functions are, they're a stretching of sine and cosine, but not uniformly. So let's look at how much u is stretched by. It's stretched by R over A. du is R over A d theta. Delta u is R over A delta theta. So there's different stretching depending on the theta. So let's look at the stretching of u for different values of k. It's hard to see much happening for the small values of k, but then it starts to happen quickly, and yeah. And again, there's the most stretching at phi equals pi over 2. That's where u is stretched the most. And again, I only went to 0.96. So u is stretched, almost no stretching at 0 and pi. So this is how u gets stretched. I graphed it both along so you can see with the phi, but then also just vertically so you can see the stretching that way. Again, if I look at b over a for the ellipse, and this always goes to pi over 2, that's where the maximum stretching will be, right here at the green. So at 0.96, b is it's actually 25 over 7. So a nice little Pythagorean triple there. So to see how this stretching changes the graph, and we'll get sun u and kun u. Well, I'll start with sun u. So sun u, if k is 0, sun u is just sine. And the maximum stretch is this value here, b over a. So there's no stretch at all. Everything's stretched by 1. So if we want to see the stretching even better, we can look this way. So we can see the stretching. So we've got a maximum stretch where the phi equals pi over 2 and 3 pi over 2 occurred. Not much stretch where phi equals 0 or pi. In fact, if I do it quickly, if we keep an eye on the points near u equals 0, they don't seem to move much at all, but because they're not stretched much. So it's pretty easy to see where the most stretching occurs. This is with 0.96. If I go to 0.8, again, not a little less stretching, but so then the maximum stretch is at 1.667-ish. So if you look at the values there, so I'm seeing u now on the horizontal axis. So these points are stretched, and these are not too much. And again, the stretch amount for each of those intervals, because there's 80 of them, there's also, so I looked at everything in terms of the 80 subintervals of 0 to 2 pi. So the max stretch is just about 5/3, and the min stretch is just over a little teeny bit more than 1 when k is 0.8, which this graph's for. This is now the horizontal axis, so how much u gets stretched. Again, that's all based on this. So the average r is 1 here, and its maximum here. The most stretching for any k is going to be at phi or theta equal pi over 2, 3 pi over 2, and almost no stretching at phi equals 0, pi, multiples of pi. And odd multiples of pi over 2 has the most stretching. So similar idea with cosine. If k is 0, this is the graph of cosine, and now we're going to stretch it, but not uniformly. We stretch it more at phi equals pi over 2 and 3 pi over 2, but this is where cosine is 0, so it'll be different than the sine being stretched. Sine got stretched at its max and min of 1 and -1. Cosine gets stretched at its zeros, the maximum stretch. So stretch, 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 and so maximum stretch at the zeros. Hopefully you can see that. If I do it quickly, you see almost no stretch on the left. And then, of course, there's like no stretch here at the other peak. So no stretch there, maximum stretch here. And we can see the stretch amount is going to be by b over a. All right, so that was a long video, but hopefully you gained some understanding of the Jacobi elliptic functions and their graphs. So I guess I'll finally wrap it up here for at least this video. I do want to get into, there's another popular way to define the Jacobi elliptic functions with a horizontal ellipse. So I'll look into that and compare the two. They have different integrands, so I'll have to resolve that problem. And then we'll also look at differential equations that the Jacobi elliptic functions solve, and in particular solving the pendulum differential equation. Might do that a couple different ways. So, all right, yeah, I guess enough for this. So thanks if you were able to make it through, and hopefully you found it worthwhile. Also, I put a lot of documents in the description. Hopefully they will be beneficial to you as well. Thanks again, and have a good day.